Hello and welcome to our Leaving Cert physics lesson. This is our second lesson on force. To begin with, let's recap what we did in the first lesson. In our first lesson, we defined what force is. So we talked about what it actually is and what it means. And we said that force is, first and foremost, an interaction. Okay, so not something that can be seen or touched, but we do observe the evidence of it. And that is what a force results in. So a force causes an object to accelerate. So force causes acceleration. And what does acceleration mean? It means that an object changes its motion. Okay, so perhaps it gets faster, perhaps it gets slower, or perhaps it moves when it didn't move before. So a change in motion could be a change in speed or velocity, or it could mean a change in direction of the motion. And an object has no reason to change these things unless they experience a force. And the force would be felt as a push or a pull. Okay, and we also mentioned that the unit of forces is the Newton, or letter N, named after Sir Isaac Newton, who we'll meet later in the lesson. Now, we also talked about something called net force. So, net force was when you add up all the individual forces acting upon an object. And if all of the forces add up to zero overall, so they cancel each other out, the net force is zero. And if that is the case, there will be no acceleration of the object. That means its motion will not change, and it doesn't change for no reason. We went on to list and speak about different types of forces. We mentioned an applied force. That's like a push and a pull as a result of direct contact, so kicking a football or pulling a rope. That is an applied force, and it will result in a push or a pull and therefore acceleration. We mentioned weight, which is the word we use to describe the force due to gravity that an object experiences. We mentioned friction, which is an opposing force and works against the motion of an object or to slow it down. We talked about elastic force. So when an elastic material is stretched or squashed, it will spring back to its original shape, and in doing so it can push an object forward and exert a force on it. We mentioned electric forces, how a battery can pull electrons around a circuit and therefore giving us current. We mentioned magnetic force, the way two north poles can push each other away. And we mentioned the normal force. Okay, the normal force was a little bit different to think about, but we decided that it must be there to give us net force 0 against gravity when we are, for example, standing on the ground or on the floor of the classroom. Why do we not fall through the floor? Well, there must be an equal and opposite vertical force to cancel out the force of gravity, and we call that the normal force. And then lastly, in the previous lesson, we looked at some force diagrams. I'll just do one example quickly. Let's take a car accelerating forwards. Okay, I'll draw my best car here. Alright, and a question in an exam might ask you to indicate the forces acting on a car accelerating forwards. So if this car is accelerating forwards, well then there must be an overall net forward force, and we'll call this the forward force, and this would be as a result of the drive of the engine. Okay, it's in contact with the road, we assume, so there will be some friction, but this friction must be smaller. I'll call it just F, okay, FR perhaps for friction. It must be smaller than the forward force if the car is accelerating forward, and as with everything on this planet, we will experience the force due to gravity, or W for weight, and the car does not move up or down, so that must have an equal and opposite normal force. Okay, so there's the force diagram. Now, what will we do today in this lesson? Well, we're going to look at Newton's 3 laws of motion. Okay, we'll speak about each of those. You're going to do a worksheet based on Newton's second law. And we're going to prep for your experiment on Newton's second law, which will take place on Thursday. So if you're properly prepared, you can start into that straight away on Thursday. Okay, so let's go ahead with that. So here we have him, Sir Isaac Newton, and a very famous quote from him: "If I have seen further than others, it is by standing upon the shoulders of giants." And we think he refers to those many scientists and explorers of thought that came before him. So he has laws of motion, and there are 3 of them. So we will discuss those now, and I think you'll find that they come across as very common sense, and I guarantee you have heard of at least one of them before. So here's Newton's first law of motion. The velocity of an object does not change unless a total external force acts upon it. Now this is complete common sense. Why would an object change its motion unless it is feeling a force? So it must be when the net force is not equal to 0. And the example I give is a football sitting on a pitch will not move unless it is given a kick. It would have no reason to change its motion unless it is given a kick. So that's Newton's first law of motion. You'll find it on your definitions page also. Newton's second law of motion then. When a total external force acts on an object, the acceleration caused is proportional to the force and takes place in the direction of the force. So what does this say? So let's pick out some words. When a total external force, now that just means when you add up all the little forces and there's an overall force, that's their net force. And so the net force is not equal to 0. The object is experiencing a force. Well, then an acceleration will happen. We discussed this before. And the acceleration that's caused is proportional to the force. That's the first thing. So it means if there's a large force, then you'll get a large acceleration. And if there's a small force, a small acceleration. And secondly, it takes place in the direction of the force. So if the overall force is coming from left to right, well then the object will accelerate left to right. So if you're pushing something from left to right, it will move left to right. Also, the acceleration is inversely proportional to the mass of the object. So here's a mention of mass. Okay, so mass is how many kilograms the object is, and inversely proportional means that if you have a large mass, you'll have a small acceleration. So a big heavy object is hard to get accelerating, and if you have a small light object, you'll have a large acceleration. It's easy to accelerate it. Or in symbol form, sorry now I've crossed over there, A, the acceleration is firstly proportional to the force on top, and secondly inversely proportional to the mass. If you rearrange that slightly, okay, that if you multiply both sides by m, you get F, and this proportional sign changes to an equals. I'll tell you why in a moment. F equals MA, and so this you'll become very, very familiar with, and it's quite famous. Okay, and where we can change the proportional sign to an exactly equal to sign due to the definition of the unit Newton. So F equals MA is what you need to take away from this. If you're asked to what is Newton's second law of motion, you have a choice. You can reproduce this first sentence, which you'll find in your definition page for mechanics, or you can produce it in formula form here, F equals MA, and say what F is, that's the force, M is the mass, and A is the acceleration. Okay, so what does it all mean? Let's take the example of the football again. When a football is kicked, so it is kicked, there is a force, there is a total external force. The acceleration depends on, firstly, how hard the football is kicked, so that's how big the force is. So it's proportional to the force and in which direction the football is kicked. So if you kick it towards the goal, it should move hopefully towards the goal. And then the heavier the football, the smaller the acceleration. Okay, so if you have a big, heavy, wet Gaelic football, you kick it, there's not so much acceleration versus a beach ball that is very light. Okay. Now, Newton's third law of motion, and I'm sure you've heard of this, for every action there is an equal and opposite reaction. For example, a rocket's engine exerts a downward force on the ground, and the ground exerts an upward force on the rocket, and there's a force acting upon the rocket, therefore there will be acceleration. The upward force gives upward acceleration, and the rocket moves up. Okay, so those were Newton's 3 laws of motion. You can be asked them in the exam, so learn them from your definitions page, and also you need to know which one is number 1, number 2 and number 3 because they don't give you clues. So this one means when a football is kicked, the foot exerts a force on the ball and the ball exerts a force on the foot. So next for you to do is the problems worksheet, or you can do it when this video is completed. So you'll be given a copy of it, and it'll also be available in our team. And the problems are all based around Newton's second law. The formula you will need is F equals ma, that's force, mass and acceleration. And I'll provide the solutions a little later on in our team so you can check your answers also. This is the sheet in case you're trying to locate that, and the questions will require you to use one of these 3 different versions of Newton's second law, force equals ma. So you'll choose the one that suits the question you are being asked. Now, following that, we want to prepare for experiment on Thursday, and this experiment is based on Newton's second law, and you're required to prove that A is proportional to F, so the acceleration is proportional to the force. So we're going to use our ticker tape timer for the last time, and we're going to apply a force to our trolley and we're going to measure the acceleration. Okay, so have a look there at that picture. What's new in this scenario that wasn't in previous experiments is this pulley here, this pulley system, and this weight, which is the applied force. So we're pulling the trolley down the ramp, and it's going to accelerate. So we're going to change the force here and see and measure the accelerations from our ticker tape. Okay, and we'll see as we add more forces, we'll get a bigger acceleration. Okay, and what we hope to do at the end of it is to draw a force versus acceleration graph. If we want to prove that they're proportional or there's a pattern or a trend, we hope that we get a straight line graph. Okay, and that's it. For revision purposes, you should revise, I think it was experiment 2. And that's how to measure acceleration. Okay, so revise that. I'm also going to post a video of this experiment so you can watch that through a few times. And you can begin the write-up of your experiment in that you can fill in the title, the date, the diagram and the procedure section from the video that I'm going to send you on that. Okay, that concludes our lesson for now. So what must you do next? So first I want you to do the problems worksheet based on Newton's second law, F equals ma. Second, I want you to watch the experiment video. The link will be in our team. And third, I want you to begin the experiment report. That is your title, etc., your diagram, and you can write your procedure. And then we'll be ready to go on Thursday with your experiment. Thanks very much.